Continuing in Mod 13, we're going to talk about expanding and condensing logarithmic expressions. So this is just our way of taking some big clunky expression or big argument and breaking it down into lots of little logs. And if we have logarithmic expressions that have a small statement as their argument, then moving forward towards calculus, it's far easier to differentiate and find the integral of. Okay, so in calculus we do a lot of derivatives and integrals, and they're much easier to deal with logs and log expressions when they're written as concise small pieces as opposed to one big log. So we're going to make sure we know our product, our power, and quotient rules of logs from the previous page. So these last three, because we're going to be using those a lot here. So we need to expand a logarithmic expression. And I want you to think about what we're doing is we're unwrapping it carefully. So imagine your grandmother has a package and she goes, oh, this is some beautiful wrapping paper and I want to save it for later. And she peels it apart very slowly and carefully, making calculated moves. So we kind of do the same thing here. We're going to smooth it out and spread this out so it's nice and smooth and easy to deal with. So in this first example, in section D, example 4, we have to look at what is going on inside of this logarithm. And so between that 25 and x squared, we have a product. So using the product rule, I can separate this and I can write it as two separate logs. Each of those factors in my argument now becomes their own argument, and there's a plus sign between them. That first logarithm, log base 5 of 25 is equal to 2. And then the second piece, because we have that power, our power rule lets us put that in front, so I can say this is 2 times log base 5 of x. And technically this is done, but we always want to think about factoring out a GCF if we can. And both of my terms have a 2, so I can factor that out, and I've got 1 plus log base 5 of x. So this would be the fully simplified form here. The one above is acceptable, but moving ahead and progressing in our math studies, we just always want to think about factoring a GCF or factoring anything, because when we start having rational expressions, we need to remember we can cancel common factors. So, example 5, natural log of x divided by e to the x. So, this is our quotient rule. And our quotient rule says I can take this and spread it out and write it as 2 separate logs, and they'll have a minus in between them. They'll still be logarithms of the same base. So I've got natural log of x minus natural log of e to the x. And that x can come in front. So this is the natural log of x minus x times the natural log of e. And the natural log of e is equal to 1 because the base and the argument are the same. So here we end up with the natural log of x minus x. And just to be clear, that natural log of x is one term. The minus x is separate. So natural log is an argument on the first x. We would calculate that and then subtract whatever value we had for x. And so now we're looking at example 6, which I'm sure looks quite daunting to some of you. But again, you just think about peeling away the layers. So the first thing I'll do is I'll take this cube root, and we can write cube roots as a rational power. So I'm going to rewrite this and say, all right, well, I have log base 4 of this big expression, and that is x cubed. I'm also, as I do this, I'm going to take this square root and write it as a rational power. So the cube root as a rational power is going to be 1/3, and the square root is going to be 1/2. So I have x cubed times x minus 7 to the 5th. And that to the 5th is going to be divided by 2 because that's my 1/2 power for the square root, all of which is over x plus 2. And then everything in my parentheses that was originally under that cube root is now to the 1/3 power. Okay? So that 1/3 power can come into the front, and I have 1/3 log base 4 of x cubed x minus 7 to the 5/2 over x plus 2. So as I'm looking at what I have in my current argument right here, the messiest thing about it to me is the fact that we have a big fraction. So I'm going to use my quotient rule. And when I do that, what I end up with is 1/3. And that 1/3 is going to be in front of everything as I expand it. So I'm just going to leave it in front now, and I'll distribute it at the end if I need to. So I have 1/3 log base 4. The numerator is x cubed x minus 7 to the 5/2 power minus log base 4 of x plus 2. So I had a big rational expression in my argument, and that fraction bar became this minus. And then also we want to notice is that that 1/3 was in front of this, so I had to draw these square braces to help me remember that it's going to distribute to everything on the inside eventually, if that's how I determined to do this. So we have another step looking at what we have. This last piece, we don't have to deal with it. Log base 4 of x plus 2, because that's not the log of a product or the log of a quotient. It's the log of a sum, and we don't have a logarithm sum rule. So that term is going to stay where it is. But my term in the front, we're multiplying between that x cubed and the x minus 7. So in this situation, this is going to be the log of a product. And the product rule says when I separate this into two logs, I'm going to put a plus for each of them. So I have 1/3. This becomes log base 4 of x cubed plus log base 4 of x minus 7 to the 5/2 power. And then that minus log base 4 of x plus 2 is still there. So I have two more properties. Well, one more property I can apply, and I can apply the same property twice. We have some powers here. So I have a power x cubed, and then I have this argument x minus 7 to the 5/2 power. And both of those powers can go in front of each of their respective logs. And since I'm running out of space here, I'm going to erase and input as need be. But this x cubed, this is now going to become 3 log base 4 of x. And my log base 4 of x minus 7, that 5/2 is going to go in front here. So I'll erase that. And when the 5/2 comes in front, I'm left with log base 4 of x minus 7. And so now I've written these all as nice, easy to deal with logs. And if we pay attention to, each of these expressions, they're pretty simplistic, which makes them easy to deal with, especially moving forward to calculus. And then the last thing we might want to talk about here is that 1/3 could distribute to all of these terms. But of course, we like to leave things in factored form when we can, so I'm not going to do that here. So my final answer on this problem is this piece right here. Okay, so not only can we expand, but we can condense. So we're going to go the reverse order. And moving in the reverse order, I wish I could tell you always are going to use the properties in the same way, but you're just going to think about repackaging. So what we previously did was we unpackaged, and now we want to carefully put everything back in the box, right? So in example 7, part E, we're going to put each of these coefficients in front of our logs into the power. So this is the same as writing log base 5 of x cubed plus log base 5 of y to the 4th minus log base 5 of w to the 1/2. And remember that 1/2 power, we can take that later and write that as a radical. So when we're dealing with rational exponents, any value, that could be written as an nth root of b. Okay? So I have a product rule in here, which lets me smush those first two logs together because we have a plus sign in there. I'm going to use my product rule, and that's going to become the log of x cubed times y to the 4th. So this is log base 5 of x cubed y to the 4th minus log base 5 of w to the 1/2. And then we have a minus here. So the minus implies the quotient rule. So as I condense these together, I'm going to have a numerator divided by a denominator. So this becomes log base 5 of x cubed y to the 4th over w to the 1/2 power. And I'll write that a little nicer over here. We've got log base 5 of x cubed y to the 4th over w to the 1/2 power. And a 1/2 power can be written as a square root. So I've repackaged this. I took my expanded version and condensed it down to a single logarithm. And so for our last example in this video, example 8, we're going to repackage 2 times the quantity, natural log of x to the 4th minus 5 natural log of x, plus 2/3 of natural log y to the 9th, minus natural log of y. So we want to make sure that we're paying close attention to those parentheses. And, we do want to consider our order of operations and how we're going to smush these back together. So because I have this 2 in front of the parentheses, I want to kind of condense what I have in the parentheses here first. So the 5, that can be a power, that's going to be x to the 5th. And the minus is going to be a quotient. That means I can say x to the fourth over x to the fifth. And x to the fourth over x to the fifth, that's what I'm going to end up with in my argument, condenses to just 1 over x, or rather x to the negative 1. So I have 2, the natural log, and that we said was going to become x to the negative 1 plus the 2/3 ln y to the 9th minus ln of y. So at this point, I've got 2 powers that I can pull up into each exponent. So here, I have the natural log of x to the negative 2 plus the natural log of y. So that becomes 9 to the 2/3 power, right? And so power to a power, we multiply. 9 times 2/3 is 6. And I've got minus the natural log of y. So thinking about condensing these together, I have a plus and a minus. Plus means I'm going to multiply those 2 logs, and the minus means that y is going to go into the denominator. So this becomes the natural log of x to the negative 2, y to the 6th over y. Because we multiplied x to the negative 2 and y to the 6th, and then we divided by that y value. I'm going to erase over here some of my scratch work that I did. And this we can simplify. The x to the negative 2 can go into the denominator and become positive. And then y to the 6th over y is going to be y to the 5th. And since that's positive, it'll remain in the numerator. So my final answer here is I end up with the natural log of y to the 5th over x squared. And I have condensed that to a single log. There should only be one logarithm in your final answer. So as you're using those properties to expand and condense, just be careful, make sure that you are writing them out correctly. When you take 2 logs and condense them together, there's only going to be one log written there. So we have a couple more examples before we move on to solving. We can use properties of logarithms to evaluate expressions. So in this case, I can condense this and make this easy for me to deal with. So the power, this is the same as log base 6 of 3 squared. That becomes 3 squared, which is 9, plus log base 6 of 4. And then because of the plus sign in the middle, I can multiply those. So this becomes log base 6 of 9 times 4, which is 36. So in this situation, 6 to what power equals 36? My answer is 2. Similarly, for example, 10 natural log of e to the 8th minus 3 natural log of e to the 4th. So I can use my power rule for that 3. That gives me the natural log of e to the 8th minus the natural log of e to the 4th cubed. Power to a power we multiply, so this is going to become e to the 12th. And so one of our properties from a previous slide, when the base of the log is the same as the base of the exponential term in our expression, our argument, those are going to reduce out because natural log is base e, and we're dealing with e to the 8th. This guy becomes 8. and the other term will become 12. So 8 minus 12 is negative 4. So a little bit more conceptual thought process. Log base 2 of 7 plus log base 2 of x equals log base 2 of 35. So this leads us towards solving equations, which is going to come next. So since we have a plus sign in the middle of these two logs on the left, the plus means we could use the product rule. We could rewrite this as log base 2 of 7 times x equals log base 2 of 35. So 7 times x, whatever's in there must equal 35. And so what we can determine here is that 7x equals 35, or rather, x must equal positive 5, because 35 divided by 7 is 5. Example 12, natural log of x minus the natural log of 4 equals the natural log of 3 over 4. So our minus that we see here would be the quotient rule. And the quotient rule means I can take this and rewrite this as the natural log of x over 4 equals the natural log of 3 over 4. And you should be able to see that now we're dealing with an x over 4 equals 3 over 4. In this case, x is going to equal positive 4. And lastly, negative 2 log base 8 of 3 equals log base 8 of x. So that negative 2 can come up into my exponent. Log base 8 of 3 to the negative 2 equals log base 8 of x. So my argument on either side, I have 1 log equal to 1 log. We can suppose then that 3 to the negative 2 equals x, and 3 to the negative 2 is 1 over 3 squared, or 1 over 9. And we're done. One more video to come.